Today's lecture is going to be about finding polynomials if we're given the zeros of the polynomial. Last time we discussed that if you're given a polynomial, then you can find the zeros of it if it's given in a factor form. So now, for example, if you're given a polynomial x minus 2 times x minus 3 times x minus 4, and they ask you what are the zeros of this polynomial f of x, then you would say either this is 0 or x minus 3 is 0, therefore x minus 4 is 0, therefore the solution that you will get is x equal to 2, x equal to 3, and x equal to 4. So if we can factor a polynomial, then we can find the solution to zeros of that polynomial. The reverse is true as well. So if I give you the zeros, could you go back and find the polynomial? The answer would be yes, but it might not be a unique polynomial because you can raise these exponents to the power 3, 4, 5, and so on. It changes the multiplicity, but it's not going to be a different zeros. So you'll get the same zeros, but with different multiplicity. And you can multiply constant in the front. You can multiply a 3 here. You can multiply 13 there. It doesn't affect the zeros. The zeros are fixed. So normally, if you can write a polynomial as a constant a, maybe I should highlight that, a times x minus c1, x minus c2, x minus c3, and so on up to cn. We say ci, these guys are zeros, are zeros of f. And if there is a different multiplicity, you say to the power m1, that's multiplicity 1, multiplicity 2, and multiplicity n. We're not going to focus on the multiplicity. We're going to decide, okay, if you're given the 0, can you figure out what the polynomial is? And what is a? A is just a rescale of the polynomial. So a is a leading coefficient, if you remember from last time. Okay, so for example, if given given x equal to 1 and 2 as zeros of f, as zeros of polynomial of f of x, can you find f of x? Okay, the answer is very simple. You can say f of x equals x minus 1 times x minus 2. Because now, if I ask you what is the solution to this polynomial, you would say x minus 1 equal to 0, therefore x must be 1. And we will get this solution, x minus 2 equal to 0, therefore x must be 2. I will get the other solution as well. So this is the polynomial that you're looking for. Is it a unique polynomial? Not really. I can say this is another polynomial, minus 2. Let's say 12 times that. It still has the same two solutions. How about if I say f of x equals negative 5 times x minus 1 times x minus 2? Still, this polynomial has the same two solutions. F of x equals negative 5 times x minus 1 to the power 3, x minus 2 to the power 7. Same thing. The only difference is here, the degree for the first polynomial. Here, let me show you this. If I ask you what is the degree here for the first polynomial, you'll say the leading term here is x, leading term here x times x, degree x squared. That would be the leading term. In the next case, the degree of the polynomial, again, would be 2. This is the degree, is this exponent. The exponent corresponds to the leading term. So what would be the degree in the second case? The second case, again, you will have leading terms x, and this constant 12. You will get 12x squared, but the leading term is still 2. In the third case, degree would be again 2, but the leading term would be negative 5x squared. Leading term is 2. In the fourth case, what you get is the degree is negative 5 times x to the power 3 and x to the power 7. So what do you get as negative 5x to the power 10? You'll get a polynomial with degree 10 not to the second degree. So to make this polynomial quite a bit unique, normally they will tell you what is the degree, and normally they give you the smallest degree possible. Otherwise, you have a choice to pick either 3, 5 here, 5 the other way as well. So if they don't tell you the multiplicity, you assume this or degree 1. So here, to make this polynomial to be a unique polynomial, I'll say given x equal 1 and 2 as a 0 of f with degree 2, with degree 2, then find f of x. And then I would not have this last case. And the only difference between the other terms is this constant up front. Here was 1, here is 12, and the third case is -5. And if I tell you that the coefficient with the leading term, with the leading coefficient, for example, 5, then you should pick the third case. Put 5 up front and say, okay, that is the leading coefficient, therefore the solution would be this polynomial. Let's assume this is +5, not -5. Maybe I should change it to -5 just to be with the leading coefficient -5. Since this was originally -5 here. Okay. So the leading coefficient helps make it a unique polynomial. So let's try one more example. Roll down here. An example. Find polynomial f of x with zeros of degree, let's say f of x of degree 3 with zeros 2, -√3 and √3. And if I don't give you the leading coefficient, you can pick leading coefficient to be any constant. So sometimes they don't give you the leading coefficient and you want to pick 1, for example. So here in this case, I'm going to tell you f of 0 is given 1. This is an extra information. I'm going to come back to this just to show you that what does this do and how does it give you a unique solution. Okay, so first let's assume leading coefficient is 1 and we try to solve this question. Okay, so what would be f of x? F of x must be x minus the solutions 2, x minus -√3, and x minus the other solution +√3. And I assume that the leading coefficient here, again, I picked the leading coefficient uniquely to be 1. It could be any number. I could pick 12 here. If they don't give you that leading coefficient, it's an option. You can simplify this polynomial. If you distribute and simplify, let's say if I do that, I can rewrite this. I can multiply these parentheses to each other. First I will do this. Distribute that and simplify this. What do you get is f of x would be x minus 2 times. Normally you don't want to have square roots and stuff involved. So if you distribute, you will get x squared. -√3 times x will -√3x, and you'll get +√3x. Then they will cancel out, and you'll get x squared minus 3. If you distribute that, this is what the end result would be. And again, you can continue by multiplying. If I distribute now this one and combine like terms, I will get x cubed minus 2 times x squared, x times -3, -3x plus 6. So this is the polynomial that has all those 3 solutions. This polynomial. It's the same as this one, the same as the one before. This is just distributed version of the original case. Either way is acceptable. Sometimes in the homework they might ask you to simplify it, so this would be a better choice. Okay, so now this is your solution. It's not a unique solution just because of that leading coefficient. What if I tell you that f of 0 is 1? What does it mean? That means if you replace 0 into the function, what do you expect is 1? So if I replace 0 here and say, let's calculate 0, you get 0 cubed, which is 0, minus 2 times 0 is 0, minus 3 times 0 is 0, plus 6. What did I get? I got 6. It's not what is given. What is given is f of 0 equals 1. But here I got 6. So how do I fix it? I fix this by rescaling. The only thing that I haven't picked normally in this case is the coefficient. So how do I fix it? I'll pick the coefficient to be 1 over 6. If I do that, when I get the solution 6's value, then 1 over 6 times that makes it times 1 over 6. I'll get 1. So this f of 0 equal to 1 is an extra information to figure out what is that leading coefficient. In this case, if I don't pick the leading coefficient to be 1 over 6, then the f of 0 is really 6, it's not a 1. Okay, if this was given 6, then the leading coefficient should have been 1, because we don't need to pick any other number. Okay, normally they only care about leading coefficient 1. They do not ask you to do that. But if in case you see something like this, you can always try to rescale the function just to figure out what is that initial condition. Okay, let me show you one more example. Sometimes, let's say given these zeros, x equal to 1 minus root 2 and 1 plus root 2. They ask you to find f of x with the degree 2. Find f of x with degree 2. Here, f of x would be x minus 1 minus root 2 and x minus 1 plus root 2. Okay, this is your solution. This is the result. X minus both solutions and their product. And since I didn't really care about the leading coefficient, the only thing is that you need to be careful here. If they ask you to simplify, you should distribute this negative sign first and say this is x minus 1 plus root 2 times x minus 1 minus root 2. And then distribute all these into each other. There's a shortcut to it, but I don't want to get into how to do the shortcut. I just want you to make sure that you do the calculation correctly. You distribute all those and they will cancel out with each other. Try this at home, see if you get the same result. If you calculate this one, the result should be x squared minus, let's see if I can do this in a shortcut way. X minus 1 squared equals 2. So I'll get x squared minus 2x plus 1 minus 1. I expect this to be end result after you calculate, after you multiply and simplify. So if you do that, let's see if you get this answer. Okay. I don't want to go through the shortcut process for you guys. You should distribute and calculate. Okay, so factoring is quite useful to find the zeros. Sometimes given a polynomial, they ask you to divide two polynomial into another polynomial, and that helps with the factoring. For example, if they ask you to divide, let's say 72 into 2, what would you do is say, what number multiplies by 2 gives you 7? It would be 6. 6 times 2 would be 3. You subtract these. This is 7. Sorry. I did it in the wrong order. 3. 3 times 2 gives you 6. 7 minus 6, 12. I will drag down the 2. And what is the number? 6. 6 times 2, 12. And what do you get as a remainder? 0. So if you compare this and say, What is 72? 72, this number, is basically the product of two other numbers. What are those numbers? 36 and 2. This is what you get from this division. You'll say it is 2 times 36. And do I have any leftover? Not really. So there is no remainder. The remainder is 0. But if there was a remainder, if this was 73, for example, you'll get the same thing, but with the remainder 1. Instead of 0, you would have 1. So instead of 0 here, you'd say this 2 times 36 plus that extra 1. 73 would be that. The same property holds for functions, for polynomials at least. You have polynomial f of x given, you divide it into another polynomial. What you get is a polynomial with some remainder. All these functions we expect to be polynomials. So what is f of x? F of x is product of two polynomials with some remainder, rx. The dividend, divisors, these guys multiply by each other, plus the remainder equals to the original, into the f of x. Okay, so px times qx plus the remainder rx equals to f of x. I don't remember what do we call it, so let's assume this is the notation. What is it used for? Sometimes for finding zeros of polynomials. So let's assume, for example, let's figure out how to do long division first. Let's say you're given a polynomial x squared minus x minus 6. And they ask you to divide this by x minus 3. And they ask you to figure out what is this division. So what you can do is you can go through this long division. Say x squared minus x minus 6 divided by x minus 3. You always compare the biggest term. What is the biggest term? Here is x squared, and compare it with x. What do I multiply by x to get x squared? I should multiply on x. So x times x, x squared. X times negative 3, negative 3x. And I subtract x squared from x squared. So you don't need to use parentheses as long as you make sure that you subtract top from bottom. X squared minus x squared will cancel out. So these two will cancel out. Negative x minus minus 3x. Minus 3x is positive 3x. Negative x, they will give you 2x. I'll drag down the other term, minus 6. So now I compare x and 2x. What do I multiply into x to get 2x? Positive 2. So positive 2 times x, I'll get 2x. Positive 2 times negative 3, minus 6. Subtract from each other. 2x minus 2x will cancel out. Negative 6 minus minus 6, 0. So what can I say? I can say if you divide x squared minus x minus 6 into x minus 3, what do you get as the result is x plus 2. In some sense, x squared minus x minus 6 is the same as the product of these two terms plus the remainder 0. So it is x plus 2 times x minus 3 plus the remainder 0, which in this case 0 really doesn't affect anything. So what did we do is we basically factor the polynomial into two other terms if there is no remainder. So it's useful to break down the polynomial. It's quite easy for second degree polynomials, but if the degree of polynomial is higher, long division is very useful. So you don't need to go through long division. You don't have any other option if degree of polynomial is quite high. Let's do one more example just to make sure that you know how to do long division. Let's say you're given x cubed minus 2x plus 5. They ask you to divide this into x minus 1 or x squared minus 1. Here I have one suggestion when you do long division for polynomial. Put them in order, x cubed. You see, the next term should be something x squared, but we do not have that term. So I'm going to create an extra space here. This is for the x squared term. I'll create some extra space for the x squared. Then I have 2x, then plus 5. Based on the degree, there should be something x squared, but we do not have that term. So I just leave a gap here for the x squared. For example, plus, you can write 0x squared if you want. But normally if you just write 0 is good enough. So you make sure that there is a term here. And the same here. I have x squared. I do not have any x. You can write plus 0x if you want, then minus 1. By doing this, when you compare, it's easier. Okay, now if I do the long division, what do I multiply to x squared to get x cubed? I'll multiply an x. X times x squared is x cubed. X times 0, 0. X times negative 1 minus x. Just make sure that you multiply correctly. You see now, if I didn't put this 0 here, I might have made a mistake comparing zeros in terms. Okay. Well, actually, let's change this a bit, because this came out to be very simple. Let's make this minus x or something. I just want you to see minus x plus 0. I want you to see that if you didn't put the 0 here, there might have been a mistake. X times negative x becomes negative x squared. So here you'll have negative x squared. If you don't write that 0, then you might write the negative x squared under this and compare these two together, which you cannot do this. X times 0 plus 0. X or whatever. Okay, now if you subtract these, x cubed minus x cubed will cancel out. 0 minus x squared plus x squared. This is very important that you put that 0 so you do not make the mistake. Negative 2x minus 0, still minus 2x, and plus 5. And here finally, plus 1. 1 times x squared is x squared. 1 times x, negative x is negative x. 1 times 0, 0. Subtract them. These two will cancel out. Minus 2x minus x is negative x. And plus 5. So what is the outcome of this division? The outcome is, if I divide those two polynomials, I should get x plus 1. But there is a remainder. How do I write the remainder? You cannot write plus negative x plus 5. This remainder is a fraction. It's a fraction divided by x squared minus x. When you divide 10 by 3, you don't say it is 3 plus 1. You'll say it's 3, because 3 times 3 is 9. What is that 1? 1 is the remainder. So you write this 1/3. Okay, so if you divide 10 divided by 3, it's 3 plus 1/4. 1/3, sorry, not 1/4. This is the same thing. So I can say x cubed minus 2x plus 5 equals x squared minus x times x plus 1 plus negative x plus 5. This is one way I can write it, or I can write it this way. Okay. In this case, I do not need the fraction because I haven't divided it. I just wrote it separately. I said if I multiply these two and add the remainder, I should get this polynomial. But if I divide the polynomials into each other, then I will get this term plus the remainder. The remainder is in terms of a fraction. Okay. I think that's quite enough for division. Oh, there is the other way of dividing polynomials. Normally it's used only in the case when you divide by a linear polynomial, x minus 3 in this case. And it's just the same as the long division. There is a process to calculate. Sometimes this synthetic division is faster. I'm just going to give you the structure of how to do it. If you're given a polynomial, divide by another one. And you assume that there is a linear polynomial, x minus 3 in this case, divided by x minus 3. And you set it equal to 0, what do you get as a solution is 3. Okay, so synthetic division, that constant you find that is a 0 is going to be up here. And the coefficients of x squared, x, and constant. So the coefficient of x squared, x, and constant I'm going to write the coefficients in order. 3, negative 14, and positive 15. Okay, these are given information. So how do you do this synthetic division? You drag down this constant 3 and multiply. 3 times 3, this guy times that, becomes 9. Add these two numbers together. Negative 5. Negative 5 times 3, 15. Negative, add them together, 0. So now, what are these coefficients? This last term here is the remainder. This is the remainder of the division. And this guy is the constant. I start from the left side now. From right side, I'm going toward left. This is the constant. This is the coefficient of x. And if there was another one, I will say coefficient of x squared. I'll do a larger, higher degree polynomial later. So what is the division? The result of this division turns out to be 3x and minus 5. So if I divide this polynomial by the other one, what do I get as the result is 3x minus 5. If there was a remainder, I would write the remainder plus 0 divided by x minus 3. But there is no remainder. 0 divided by x minus 3 is still 0. So I do not need that. This is the way that the synthetic division works. Here, there's another example. Higher degree polynomial. So what do you do first? Set this equal to 0. What do you get? X plus 2 equal to 0. X is negative 2. It's always the opposite number. I'll say negative 2. Raise this up front. Okay, what are the coefficients? The leading term is x cubed. The next term must be x squared, x, and constant. I'm going to put the coefficients here. 4. Coefficient of x squared, there is no x squared, so coefficient 0. X, coefficient 18. Constant, negative 7. So the long division kind of becomes too much work here. Synthetic division is much faster if you use it. Okay, so negative 2. Let's drag down the 4. 4 times negative 2 is negative 8. Add them up. I'll get negative 8. Negative 8 times negative 2. 16. 16 and 18. That's quite a large number. 34. 34 times negative 2. Negative 68. Right? I hope I didn't make any mistake in the calculation. If I make a mistake, just figure it out and fix it. I think so far it's correct. Negative 68 and negative 7 is negative 75. Okay, so what is this negative 75? That is the remainder. And this is a constant term. Coefficient of x squared. I'll go, this is constant. So if I do this division, what do I get is 4x squared minus 8x plus 34 plus, what is the remainder? Remainder is negative 75. But divide by x plus 2. This is how you write it. Okay, so this synthetic division is quite useful to do the division as well. It's quite faster actually. Okay, we can use this synthetic division for another reason, and it's to evaluate polynomials. So here, this is called the remainder theorem. It says let's say, if you have a function f of x given as x minus 3 times x plus 5. Let me show you an example, just give you the idea. And then plus 2. And I ask you, what is f of 3? Then if you replace 3, what you get is 3 minus 3, 3 plus 5, plus 2. What is 3 minus 3 is 0. 0 times whatever, this whole thing becomes 0, just because 3 is a solution to this factor form. And what is f of 3? It's simply this remainder constant 2. So the remainder theorem is basically, it says, if you factor out the polynomial and you have some left over, the zeros of that factor form, the zeros of this factor form, do not, it can be evaluated. So f of those zeros, f of 5, still exactly the same as that remainder 2. F of 3 would be still, sorry, f of -5 would be 2. F of 3 would be 2. Because the factor part will be 0. 0 times anything would be 0. So this remainder theorem could be used for calculation. So here's an example. F of x is given 3x cubed plus 2x squared minus x plus 3. And they ask you to figure out what is f of 2. One way is to replace 2 into the function and say, this is a quite easy way to do it. F of 2, it would be 3 times 2 cubed plus 2 times 2 squared minus 2 plus 3. If you do this, nothing wrong with it. You can calculate and say this is 8. 3 times 8 is 24. Here you have another 8. 4 times 8, 32 minus 2, 30 plus 3, 33. So f of 2, I should say 33. This is one way to do it, and it's nothing wrong with it. But they say you can use this synthetic division as well. And say, pick 2, and the coefficients of the leading terms were 3, 2, -1, and 3. And go through the synthetic division. Whatever you get as the remainder, that would be the answer. Let's try it. If I drag down the 2, sorry, 3. 3 times 2 is 6. 2 and 6, 8. 2 times 8, 16. 16 and 1, 15. 2 times 15, 30. Add them up, 33. What do we get as the remainder? Oh. Sorry about that. This 33 as the remainder. I wanted to highlight it. For some reason, I deleted it. Okay. So this 33 is exactly the same as what we got here. And it's all because of that factor form. You can try calculate another number. Maybe faster one would be calculate f of 1. You can calculate through the polynomial just to double check. But I'm going to go through the synthetic division. And say 1. Coefficients are 3, 2, -1, 3. Drag down the 3. 3 times 1 is 3. Add them up 5. 5 times 1. 5. Add them up, you will get 4. 4 times 1 is 4. 7. So if I do the calculation, at the end the remainder became 7. So what is f of 1? F of 1 is simply 7. And again, if you replace 1 into the function, you'll get 3 times 1 cubed plus 2 times 1 squared minus 1 plus 3. This is exactly the same as 7. Either way is possible. It's just different ways of calculation. Okay, this is enough on long division, synthetic division, and factoring. At this point, I'm going to stop here.